Welcome to this lecture where we're going to talk about the introduction to Project 2, where we're going to look at shortest path word melts. This would be broken over two different lectures. We're going to discuss the high-level ideas of Project 2. We're going to first start by extending Project 1, and then we're going to talk about a new type of location that you might not have considered before, and then we're going to look at the core algorithm breadth-first search at a high level. So let's think about Project 1, which was the two-dimensional maze solver. What if we wanted to take Project 1 and extend it so that this code now solves three-dimensional mazes? What would we need to change? Okay, I would actually encourage you to, at this point, pause the video and think among these things, the location class, the maze class, location stack class, and the driver, which of these things would have to change in order to accommodate a three-dimensional maze solver? So pause the video, think about it, and come back. Well, let's go through these one by one. Would the location class have to change? Yes, because now we would have a row, a column, and perhaps a third dimension called depth, right? We'd have to represent that third dimension. In addition, we would have to not only go right, down, left, and up, we would also have to go forward and backwards in that third dimension. In addition, we'd have to update all the methods that read and write and manipulate the location class. So the location class would have to change. Would the maze class have to change? Well, surprisingly, no, because what does a maze class keep track of? It keeps track of a number of valid locations, each of which is a location, and a location encapsulates all the information about three-dimensional maze locations. So the maze class does not have to change. The location stack class, what about that? Well, for the same reason, we don't have to change the location stack class. It only interacted with locations through the interface, and you'll notice that the interface of the location makes no mention of two-dimensionality or three-dimensionality or anything like that. And likewise, the driver itself also does not have to change. It can remain the same. So of all of these classes, only the location class needs to change. And as I mentioned, we'd add a third dimension and add these new iteration states forward and backward, and we'd have to make changes to the methods that deal with the data internally. In other words, we'd have to change the internals of those methods, but not how they look externally, right? So this is an important idea that we're getting at here, because we have encapsulated everything about locations inside the location class, and it's all restricted there. The interface of the location to the rest of the world doesn't have to change, but we could change the internals and change what it represents. So move from two-dimensional to three-dimensional just by changing the location class. What about four-dimensional mazes? Could we do that? Yes. What about five-dimensional mazes? Yes, we could make a five-dimensional maze solver. What would that mean? Well, it just means that every location has 5 coordinates, okay? Could be row, column, depth, time, and I don't know, some other dimension, right? So measurement like temperature or something like that. Doesn't matter what they mean, but the point is you can make a 4-dimensional, 5-dimensional, 100-dimensional maze solver just by adapting the location class. But what if we went a little bit further afield? What if we changed it even more radically? What if we wanted to solve so-called word mazes, or what I sometimes call word melts, okay? And this is what Project 2 is going to be about. So now a location is not a point in 2 dimensions or a point in 3 dimensions. Each location now represents a word, okay? A word is no longer a point in 2-dimensional space, but it is a sort of place that it can that the maze solver can be in, right? You could be in a word, or you could be in a different word. And 2 words are considered to be neighbors if and only if they differ by one modification, where a modification is changing one letter, inserting one letter, or deleting one letter. So here I've given you an example of a number of words. There's about, 8 words here, and they're all their neighbor relationships. So all of them are shown here. So bad and bed are neighbors because I can change the A to E or vice versa, and I get the same, I get one or the other word, right? I can't make more than one change to have a neighbor relationship. For example, bed and cad are not neighbors because I would have to make 2 changes. As you can see, I go from bed to bad and then bad to cad. right? Okay, and I can also delete or insert letters. So going from bad to barred is possible because I can insert this R, and removing the R takes me back to bad. Okay, so these are all the neighbor relationships in this quote unquote maze. And you can think about, well, how would I get from bad to read? Well, there are a number of ways, and we'll talk about different ways of doing that, but it is possible, right? So if we change the location class now to represent a word instead of a two-dimensional location, two-dimensional position, then everything else in our code for Project One still works, and that's pretty cool. You could solve these word melts or word mazes with all the code you have, just changing the location class, okay? But there were two issues that I want to bring up, which I've already sort of mentioned with Project One, but I want to highlight them here. Project One used depth first search, or DFS, and DFS is a great algorithm. It's a good algorithm, but it finds a path, but it does not find necessarily the shortest path between the start and then the end locations, as you should have seen as you went through your testing. So that's one issue, is we would like to be able to find short paths or shortest paths. And the second issue is that our DFS, our implementation of DFS was inefficient. And I've talked a little bit about this in the past because it could visit the same location many times. It could go there and then backtrack and then go there again from a different way and then backtrack and then go there again from a different way. And this made it highly inefficient. It gave it exponential running time. But that was only because, and I want to be very clear about this. This is not a limitation of depth first search at all. It's simply that I told you not to implement a way of remembering which locations the driver had explored in the past. If we had done that, then depth first search would have run very efficiently, even if there was no solution to the maze. But we're going to solve both of these problems by doing a switch to breadth first search. Breadth first search, or BFS, is an algorithm for finding shortest paths. And there might be multiple shortest paths, so it's going to find one of the shortest paths, right? I mean, it's possible that two different ways branch and then go back, and they're equally long, so it's going to find one of them. So breadth first search is an algorithm that, unlike depth first search, will naturally find for us the shortest paths. So that's solving this first problem. The second problem that we mentioned up here, we're going to solve by avoiding revisiting the same locations by keeping track of what we've explored. And that's actually going to go hand in hand with how breadth first search works anyway. So I want to comment on DFS versus BFS. These are both general search strategies, and they're not just used for mazes in data structures. These are very general search strategies that can be used widely, okay? And they differ in how they move at each step, either deeply or broadly, as the names imply. They're good. They're well-named algorithms. Not all algorithms are well-named, but these are well-named. Depth first search always goes further along whatever direction it can and whatever it prefers. And remember, in Project One, we prefer to go right before we go down, before we go left, before we go up. And it keeps going in whatever direction it can until it cannot. And in other words, until it gets stuck somewhere. And if it gets stuck, then it backs up, and it backs up by removing things from the search stack. And of course, we used a stack to order the search, and that stack also happened to be the current path. So whatever was on the stack was exactly the sequence of locations that we visited from the start to our current location in Project One. And that's the general rule for depth first search, is that that stack usually represents all the positions that we've been on our search from the start to here. Now, breadth first search searches broadly. So it doesn't search deeply, it searches in all possible directions at once, and it never backs up. So it never goes out and then comes back again like depth first search does. And because it searches narrowly and then more broadly, as you'll see, that guarantees that we're going to find shortest paths. And in order to do this search, it uses a queue, not a stack, to order the search. But that queue is unlike what we said here, where the stack for DFS represents the current path. The queue does not represent a current any path, okay? It just orders which things we explore in which order. So here is a high-level explanation of how breadth first search works, and I'll give you sort of a visual demonstration of this. And don't take this algorithm too literally. I just want to illustrate for you conceptually how it works. So at a high level, breadth first search does this. We'll start at the source location, and the source, or the start, is of course distance 0 from itself, right? If you're starting at home, you don't have to go any distance to get home. Or if you're starting at the start, you don't have to go any distance to get there. So the starting location, or the source, has distance 0 to itself. And then it iterates for I equals 1, 2, 3, 4, etc. It's going to find all the locations that it can at distance I using the distance I minus 1 locations it just found in the previous iteration. So I write this here this way. Use locations at distance I minus 1 to find undiscovered neighbors at distance I. Okay, so let's pretend that our source, or our start, is bad. Okay, is the word bad. So initially, it has distance 0, and everything else in this maze has distance, let's say, infinity. It hasn't been discovered yet. So initially, bad has been discovered with a distance of 0. Nothing else has been discovered. So this is the state of the world right now. This is the discovered portion of the world, or what we call the frontier. Okay, the queue is sometimes called the frontier. So what's on the queue right now, or what's in the frontier, is just bad, just the word bad. Now, from bad, of course, this is distance I equals 0. I can now start looking at I equals 1. What's at distance 1? Well, it's everything that's at distance 0 plus one more edge, or plus one more hop, right? So this is one more, this is one more, this is one more, and this is one more, right? So these four words, bed, bard, cad, and rad, are all distance 1, 1, 1, 1, 1 from the source, or the start. Okay, so we start here, we process this, and it tells us distance 0 gets us to all things of distance 1. And then from all things of distance 1, we can go to distance 2 for I equals 2, and that would get us to red and card, let's say. Now, there are multiple ways to get to red. Notice I could have used this link or this link, but I'll just use those two for now. That'll be clearer why in the next lecture as we talk about more things. So these are distance 2, and now you can see the frontier is everything that's within this region. So initially our frontier was everything behind here, right? That was our initial frontier. Then our frontier was everything in here, everything labeled 1. And then our frontier now is everything labeled 2, so it's everything in here. Okay, and then from here, I can use this link to get me to read, which has distance 3. And now I've discovered everything. So I know that the distance, the shortest distance between bad and read, has distance 3. Okay, that's how breadth first search works at a high level, and we'll go over it in more detail later in the next lecture, actually. But I want to talk briefly about the correctness of this algorithm. And I want to say the first time, why does this find shortest paths? Why does breadth first search find shortest paths? The first time that we discover a target or a location, okay, any location, or the target location, whichever it is, which is on iteration I equals k, we have found a shortest path from the source. Why is that? Well, because we did not find the target on any iteration less than k. If we had found it on the ith iteration where I is less than k, then the distance would have been less than k. So it must require k steps to get from the source to the target, and this property is true for all locations and not just the target. Okay, so again, going back here, the shortest distance, if the word read is my target, the shortest distance to read is of distance 3. And I know that because if I could have discovered it in a distance of 0, I would have, but I didn't. And if I could have discovered it in a distance of 1, I would have, but I didn't. And if I could have discovered it in a distance of 2, I would have, but I didn't. But I did discover it with a distance of 3. because at each stage of this algorithm, we're finding all locations that are one more hop away from everything that we could discover with one fewer steps. Okay. So next time, what I want to do is go into more detail on breadth first search. What I've presented to you is an algorithm description that is uh, this concept of breadth first search is accurate, but it's not detailed enough, and it's not actually exactly how we're going to implement it. We're not going to do this sort of stage by stage ordering. We will do so in a different way. Let's put it that way. So it's not exactly how we're going to implement it. So in particular, the loop structure that we saw is different. So in the next lecture, we'll talk about details on breadth first search and also importantly, the data structures that we will need in order to implement project 2.